All right, 5:15. Let's get this thing started. Thanks for being patient with me for these first 15 minutes. Just trying to get some of my own stuff organized. How are y'all? Great. That's good. You missed me. Oh, that's so nice. Fantastic. I like that too. First thing, he is not in the room right now, but first thing I want to give a shout out to Zach for winning the Enzyme Speed Challenge a couple weeks ago. I think it was 42 seconds, which is pretty freaking fast. It's in the record books, roughly 42 seconds, right? I timed myself doing it, and then I messed up on one of them, and I felt bad, so I stopped. But I didn't even get 42 seconds, so that's really good. So when y'all see him, give him a pat on the back. That's awesome. And for everyone else who participated, that was great. When y'all do boards, you can study for that for boards too. Yes, let's give him a round of applause. Our champion. Second thing is, I just took boards last week, as y'all know, and the biochem section was not bad at all. If you're coming here paying attention, it's going to be a breeze if you actually are learning this and putting it into long-term memory. And if you aren't, what I would recommend doing is just going back into My Parker and just watch my test reviews. All right, just because it's everything that we've covered, and it's in 2 hours. It'll hit all the big points. And the test questions were as easy as how many NADH are produced in the citric acid cycle? Three. They are as easy as that question, all right? Like how many ATP does NADH make? 2.5, yeah, right? They rounded up to 3 for boards, but whatever. How is phosphofructokinase 1 allosterically regulated? Just with ATP, right? If we have a bunch of energy, we don't need to be going through any of those processes. So it's like boom, boom, boom. I finished that test in 25 minutes, and I probably only missed like 5, all right? And I would say like 35% of that test was probably just test 2 material. They actually had a lot of carbs on there. Oh yeah, 2 questions. It was number like 13 and number 18. Number 13 said, an alpha helix is an example of what level of a protein structure? Just secondary, right? That was the answer. And then number 18 was, a beta pleated sheet is an example of what kind of protein structure? And I was like, wow, this is wonderful. What kind of bonds bind between the purines and pyrimidines in DNA? And it's just hydrogen bonds. Y'all haven't gotten to that yet, but it's like that simple, okay? So like when you're getting to that, don't necessarily freak out that it's like, oh shoot, I haven't covered biochem since like try 1 or try 2. It's up there. Just watch my reviews. Pay attention to board reviews. If you go to that, it's going to be not that bad at all.
How many questions were on the biochem exam?
All the questions are 90 questions, 75 minutes, and they'll toss out 10 of them. 10 of them are just like, let's see how y'all do. It's like experimental. So biochem for boards, don't freak out about it. Apparently everyone like thinks it's their worst one, but then they end up, it's like their best one, because some people just apparently didn't learn it all in the first place, so they get like 20s on that test.
What was your
Hardest
hardest one?
one was micro or path for me personally, because that's all just, did you memorize it? Did you memorize that buzzword, or did you not? So when y'all get to micro next try, put some work into that class, all right? Don't just go test to test. I think that's the first time that people start going like test to test, where it's like, okay, I'm just going to learn it for the test, dump it, and like move on. Don't do that. Try to put that into long-term memory. It's a recurring theme. Try to put it into long-term memory, right? Last thing, just something for y'all to think about. I was watching a Joe Dispenza TED Talk. If y'all know who Joe Dispenza is, y'all need to get into the library and where there's that stack of DVDs, right, with all the Parker, it's got all the Parker seminar speakers, and they've got all these other great speakers for chiropractic. Let's see, DeMartini is there, who's coming to school, right? He's coming to school next week. Y'all see about that? Y'all hear about that? Y'all seen that on Facebook? Y'all know who John DeMartini is? Oh my God, that guy's a rock star. He like lit my fire in Try One. Go check out one of his videos. Come to that assembly, not even assembly, he's coming I think on the 29th. Schedule that. You need to go to that, okay? People pay like hundreds of dollars to hear him speak, and he's coming to our school for free. So, like, really big deal. Anyway, so what I was listening to Dispenza talk, and he asked the question, how many people are trying to like improve themselves, right? So he just asked the audience, and so everyone's like, oh, like of course, like I'm trying to improve myself. And so he's like, okay, so how many of you are like know there's ways that you can improve yourself? And so everyone like raises their hand, like, yeah, I know like what I could do to be like making myself a better person. And then he says, well, how many of you people are actually doing those things to make yourself a better person, right? And so that's less hands went up. So he's like, all right, so there's already this imbalance just within your life of you're trying to be a better person, you know there's things that you can do, but you're not tackling those head on for whatever reason. So I don't have the answer as to like what that is, and he's still trying to figure out that answer too. So if you kind of have a reason, or if you have an idea for like why that might be, just at the end, like come talk to me because I'd be really interested in figuring that out. But something to get you working on like how can I be a better person and how can I start taking action steps to doing that, right? Because we're all kind of in that same boat. Like I know I probably shouldn't eat I shouldn't get the Cajun pasta, right? I should probably get the salad with the grilled chicken. Cool. Oxidative phosphorylation. Sorry, like a little bit of an intro, but just kind of wanted to share that with you. Chapter is not that bad, okay? This one's not that bad. The next one's not that bad. The hard part with test 3 is he kind of just goes through it pretty quick, right? He's already on chapter 14 or 15, and you're like, holy crap, like where did that happen, okay? So not that bad. I'll try to make sure I'll highlight the key points, and I'll tell you, I'll mark in there too, like if this was a national board question or not, just so that you can kind of have that idea of where those are. And I think Dr. Sarkar tries to do that too with you. So whenever he has like an MBQ, I make sure I write that in my book. Oxidative phosphorylation. All this whole process is talking about is we've made our NADH, right? We made it. We made the 2 in glycolysis. We made the 3 in the citric acid cycle, or 6 if we double it. And we made the FADH2, right? We're taking those hydrogens and we're taking them to the inner mitochondrial membrane of our mitochondria, and we're going to create a proton gradient. So we're going to transfer those hydrogens, and we're going to create like a proton gradient at the top, and then at the very end there's going to be some kind of magical machine type deal that's going to make ATP. And that's how, it's kind of magical. It's kind of cool actually. I don't know a lot of the details. My friend does. He said that we could Skype him in to like teach it, but you don't want that. He took like way too much bio in undergrad. But so we're going to make our ATP here, and we're also going to reduce oxygen to become water. That's mainly what this chapter is about. So we're making ATP by transferring those NADH, FADH2 into the inner mitochondrial membrane, and oxygen is going to become water, and we're going to keep living. And that's all this first page is saying. Glucose is completely oxidized to CO2. And that happened in the citric acid cycle, right? We released the 2CO2 with alpha-ketoglutarate dehydrogenase, isocitrate dehydrogenase, right? So glucose is oxidized to CO2 through those things. And in that process, we took off some electrons, and those electrons are going to go make ATP. Here's our general equation for what our overall process of glucose oxidation is going to be. We've got our glucose, C6H12O6, plus oxygen. We're under an aerobic state. It's going to make CO2 and water. What's important is that, what is it? Ooh, where'd it go? We don't directly reduce oxygen. Okay, he makes a big deal about this. And so we don't just take the hydrogens that are on glucose or that are on water. Oh, no. We don't just take the oxygens that are on glucose and put them onto the oxygen. Okay, so what we did was we put them on the NAD. We put them on the FAD, right, those intermediates. So first, we produce the CO2 and the 24 hydrogens or whatever. We can see that as NADH, FADH2. And then those hydrogens are transferred onto the oxygen to make water. So the test question is going to be something like, is oxygen directly reduced? And you're going to say no, because it's indirectly reduced to make water. And that's what we're just talking about. We have the NADH, FADH2. That's all that whole little part is saying. For those of you who are asking, hey, like whenever I see NADH, there's always like this other H, and like where does that come from? Like this is the page that does that. All right. He's not going to ask you about anything on this page. So this is kind of just for your benefit. If you're that curious person, feel free to read that. It reads pretty easily. Yeah. Let's get to the real stuff. Cytoplasmic shuttle systems. We have one problem with NADH getting into the inner mitochondrial membrane, and that's we've made some of it in the cytosol, right? We made the one NADH with what, glyceraldehyde 3-phosphate dehydrogenase, enzyme number 6, roughly. Okay? We have to get that NADH, or that hydrogen, on the inside of that mitochondrial membrane. And there are two different ways that we can do that. The first is the malate aspartate shuttle system, and the other is the glycerophosphate shuttle system. Know where these take place at. Dr. Sarkar kind of likes, in this section, he kind of likes to ask where things take place at. So if you ever see where it's at, just circle it, memorize it, put a TQ next to it just so you know. So that when that test comes up, you're not surprised if he says, hey, like where does this take place at? Malate aspartate shuttle system, and we'll get into what all those are, but those words should be familiar to you at this point, is liver, kidney, and heart, mitochondria, and the glycerophosphate shuttle system is in skeletal muscle and brain. So first off, we have the malate aspartate shuttle. And like I always like to do, I like to look at the picture first, and then we'll go into the words. Voila. Goal is to get these hydrogens from the cytosol on the inside of the mitochondria. That's it, right? How that's going to work is we're going to start here at oxaloacetate and NADH, okay? NADH is going to give its hydrogen to oxaloacetate. And when it does that, it's going to make malate. All right? We've seen malate before. It's in our citric acid cycle, right? Okay. It does that because the NADH can't just go through this membrane by itself. Okay? But this carrier right here, malate alpha-ketoglutarate, will allow malate to go through, right? So this is like say you're oxaloacetate and you're 18 and you're a freshman in college and you want to buy alcohol, right? But you can't. That's illegal. But you've got a friend who's 21 who can go into the liquor store and make that purchase for you, right? So that's all you're doing. You're giving him your money, but we would never do this, right? Because that's illegal. We would never put our friends in that position. So you give your friend your money, right? And malate then goes into the store. Boom, hydrogens within the mitochondria. All right, so we don't care. Malate isn't our end goal. We don't really want to make malate. Our whole goal is we want to take those hydrogens off and remake that NADH on the inside of the cell. So all it does is it dumps it, right? It gives you the alcohol, and now there you are, back ready to go. So now we've made our NADH. We're back at oxaloacetate. We need this oxaloacetate back on the outside so that we can keep bringing NADH into the cell. But the cell is impermeable to oxaloacetate. So what we're going to do is we're going to convert it into aspartate. And aspartate can go through this glutamate aspartate carrier, and aspartate can come back onto the outside of the cell where it can get turned back into oxaloacetate, ready to go. Overall, not that simple. Goals: get the NADH from cytosolic NADH to mitochondrial NADH. And we just kind of use like taxis to make that happen. There are a couple of, we can see here we have alpha-ketoglutarate and glutamate here, and you're wondering what those are doing. So in order to turn, let's say, we'll start here. So in order to turn oxaloacetate into aspartate, we use glutamate to do that. Okay, so glutamate helps turn oxaloacetate into aspartate, which then comes through. And then we use glutamate. Now then we use that alpha-ketoglutarate up here to turn aspartate into oxaloacetate. So it gets kind of tricky, but if we follow the arrows, so we've got oxaloacetate, glutamate is going to come in, help turn that into aspartate. Aspartate can go through this aspartate glutamate carrier. Boom, aspartate's now on the cytosol. Alpha-ketoglutarate comes in, takes off, I think it's hydrogen, and turns it back into oxaloacetate, ready to take on that NADH. What he's going to ask is oxaloacetate to aspartate requires what? And then you'll need to say glutamate. Or which of the following can go across the membrane? And the answer will be either malate or aspartate. But he likes, I think what he liked was glutamate. Glutamate turns oxaloacetate into aspartate, or alpha-ketoglutarate turns, aspartate into oxaloacetate. So just a lot of words that rhyme and sound the exact same, but just getting your head around what does what.
Are the glutamate and alpha-ketoglutarate both going through the barrier as well, or are they both just existing on either side?
Yeah. So what's really nice is that these can all be pretty much the same. These are pretty much like reused, remade. All right. So this is the glutamate aspartate carrier. So both glutamate and aspartate can go through, which is really nice. So once alpha-ketoglutarate comes and helps turn aspartate into oxaloacetate, it makes glutamate here in the cytosol, which goes through the carrier inside the mitochondria, and then helps convert oxaloacetate into aspartate over here, and making alpha-ketoglutarate, which comes back out here, and we can just keep cycling through that program.
So the only thing that really needs to come in and out of the system is NADH.
Yeah.
Put in, it comes out, keep adding in. It's the only thing that changes.
Yeah, so, yeah, pretty much. And it's all just working to get the cytosolic NADH into mitochondria NADH, just because that's where glycolysis takes place, and that's where it's made. Is that not too bad? Is that making sense? Okay. Glycerol phosphate shuttle. Short answer, yes, but I'll email him and ask him. I'm supposed to meet with him to let him know what questions were on boards. So I'll talk to him and I'll bring that up. So short answer, yes. My opinion, probably use the ones that are in the picture. Cool. Okay, so we have the same problem. We have cytosolic NADH, and we can't always use the malate aspartate shuttle just because maybe that's used up, that's full. So we have to know there has to be a different way to do it. And so here comes the glycerol phosphate shuttle system or whatever. It's the same principle, taking this NADH, putting it here, just a little bit different mechanism. So first thing that we're going to do is NADH is going to combine with dihydroxyacetone phosphate, and that's going to make glycerol 3-phosphate. Okay? The enzyme that makes that reaction happen is glycerol 3-phosphate dehydrogenase, right? Dehydrogenase dealing with an NADH makes a little sense. All right, next, this glycerol 3-phosphate, now that has the hydrogen on it, is going to give that hydrogen off and produce an FADH2 over here. So we've turned an NADH into an FADH2 within this inner mitochondrial membrane. All right, and that enzyme is flavoprotein dehydrogenase, I guess. I think that's what it is. Yeah. All right. So we've turned NADH into FADH2, and that FADH2 is then going to go take that hydrogen off and take it to our complex 2, but we'll get to that in a second. And in the process, we've remade dihydroxyacetone phosphate. So this one only has 2 steps, only has 2 enzymes. We're turning NADH in the cytosol into FADH2 in the inner mitochondrial membrane. And the intermediate is glycerol 3-phosphate.
Does that reduce the amount of ATP that you can get from it?
Yes, because that's a good question. FADH2, I don't know, I never thought of it like that. Because I don't know if like one NADH in the cytosol is worth less or more than one FADH2 there. I would assume yes, just because of that same reason. But maybe not. I don't know. Grand scheme of things, not that big of a deal. Good question, though. Good question. And all the words up here just say that exact same thing. Okay? Just know, you know the overall process, the enzyme and what it makes. Those are going to be the biggest ones. This enzyme and this intermediate of glycerol 3-phosphate are going to be the big ones. Next, we are finally in the electron transport chain, right? We finally freaking made it to oxidative phosphorylation. We spent a whole month. I've just been teasing y'all with, all right, we're going to make energy. We're going to make energy. We're finally going to do it. Big deal. Okay? But it's going to be really anticlimactic, actually. All right. So electrons are funneled into our electron acceptors. And so we have our NADH, FADH2. They're going to drop off their hydrogens. And we're going to have more electron carriers, right? That's just exactly what we wanted. We wanted more things to carry electrons. So we're going to get stuff like ubiquinone or cytochromes A, B, and C. This is a big thing. No, this was a test question for us and on boards, actually, was what's another name for ubiquinone? And it's coenzyme Q. He loves coenzyme Q. He loves ubiquinone. Loves it. And we have our electron carriers. So these are components of the respiratory chain arranged in order of increasing redox potential. That's a test question. All right, so these are ordered in increasing oxidation reduction potential. And that's how that test question will be worded, like pretty much verbatim like that. So the hydrogens are going to go through the chain of steps from more electronegative to more electropositive oxygen. And this is a test question. That one is less important, but this is for sure a test question, the order of the carriers. And we'll get to that on the next page. But just make sure that we know we're going from NADH to Q to B, C1C, A, A3, O2. All right, so it's like way not alphabetical order, which is way not helpful. If I could change it, I would, but they don't give me that power, unfortunately. So Q to B, and then C and A. And usually on this test, he makes it pretty obvious which one's which. Have you all seen? Has he done anything like in order on y'all's test, and a test 1 or test 2? And it's like usually pretty blatantly obvious. You can like at least cross out 2 of them. Yeah.
Yeah, he does that. But my question is for that order. On the next page, I know there's a chart, and FADH2 comes in, and it's like between the NADH and the Q step. Is there a reason he didn't put that on that order right there, or?
Both NADH and FADH2 are going to give to Q. So you probably could just that could be FADH2 right there, but on the
Instead of NADH?
yeah. Yeah. But I think he uses NADH on the exam, on the test, from what I remember. All right, so that's the order. Reoxidation of NADH, FADH2 in the mitochondria. That's just, we'll get to that in a second. Finally, oxygen is reduced to water. All right, I missed this on the test when I took it, and it was like the stupidest, like I said like CO2, and that was like the stupidest answer I could have put. All right, so this was a board's question too. What is the ultimate hydrogen acceptor? And it's oxygen, because it can make water. All right, so at the end of this, at the end of all of our breaking down of glucose, we are making ATP and we're making water. All right, so don't be like me and put stupid carbon dioxide. Just throw some carbons into the equation where that's like way not a thing. O2 reduced to H2O. For a review, loss of electron is oxidation, gain is reduction, oil rig. All right, and we have 4 proteins within this electron transport chain. All right, 1, 2, 3, and 4, and those pretty much go in order, so that's really nice. Yay. All right, finally, let's get to it. Complex 1, known as NADH dehydrogenase. What do you think it's going to do? We're here. NADH dehydrogenase. It's going to deal with NADH, right? It's going to take off the hydrogen on NADH, and it's going to pump 4 hydrogens into this intermembrane space, P side. P stands for positive, N is negative, so it's just comparatively, when you put a bunch of hydrogens up here, those are positive, right? Our acids. So we got more positive over here than it is over here, so that's why it's P and N. So complex 1 takes the hydrogens off and the electrons off of NADH. Complex 2 is succinate dehydrogenase. What did succinate dehydrogenase do in the citric acid cycle? Created FADH2. So we're going to use that same enzyme to take off that FADH2 and take those electrons and give it to coenzyme Q. So both 1 and 2 are going to give electrons to coenzyme Q. And like I said, we're going through that order. What's important to know here is that complex 1, 3, and 4, as you can see here, I've circled these 4 H's and the 2H. 1, 3, and 4 pump hydrogens into that intermembrane space. Number 2 does not.
In his notes, like in the written notes, it says complex 2 also drives proton transport from the matrix to the intermembrane space.
Yeah.
So that's
Yeah, that's a no. All right. I talked to him about this, and he said to go with the picture. When I talk to him, I'll re-ask him when I email also about that other question of which words he wants to know. He wants y'all to know. But from when I asked him, if I remember, when I asked him try one, he said go by the picture. All right. All right, so our electrons are taken off and given to coenzyme Q. Coenzyme Q's job is to take them to and give them to cytochrome B in complex 3. And then it's going to give it to cytochrome C1. And then it's going to give it to cytochrome C. And then it's going to give it to A. And then it's going to give it to, what, A3 is the last one? Is that right? Yeah? Excuse me. And then we're going to make water. Told you to be kind of anticlimactic. All right, so those electrons are going to be used to turn oxygen into water. Also, forgot to say it, for those of you who are interested in going to see Dr. Denise Weber, like, please leave and go do that. All right, I encourage that. You can watch this later. So her thing is at 6:30. She is a rock star. I've been to her office before and tried one, and it was a really, really cool experience. So those of you who are interested in going to like see her, like please get up and leave now and do that.
We have like 10 minutes. Yeah, we were going to say 20 minutes left.
Cool. All right. Yeah. So if y'all are going to that, like not gonna hurt my feelings at all. I'm actually going to applaud you as you leave to do that. All right. So even if like every single one of y'all got up and left, I would finish this and you can watch it later. Do I know? I don't know. I just know it's the after hours program if someone wants to say something.
But it was like a sign-out.
Oh, it was an RSVP?
Limited the number so she could talk to a smaller group. So I don't know.
Well, maybe if you wanted to go and try to sneak in too.
Yeah.
So.
She's just doing an office tour. She came and talked in neuro club. She has like pediatric chiropractic. She's big into that. And big on like the pure adjustment.
Dr. Denise Weber. It's in if you want to like jump on your, yeah, if you want to jump on your, what Alicia sends out, our weekly newsletter, and like look that up real quick. If you don't just delete those. You should read those, by the way. Anyway, so I'm going to keep, if y'all want to like just look up that, I'll keep going. All right, so we make electrons help create water from oxygen. And in the whole meantime, we've created this huge bunch of hydrogens, super positive over here, this whole gradient. And what's it going to do? These hydrogens are going to come down through this. This one's got 3 names. You got to know all of them. It's going to come down through FO, F1, ATPase, or proton ATPase, or ATP synthase. I think he'll put any of those on the test, and you don't have to know it. But it's really nice when he puts this FOF1 because it's like, boom, that's like really easy. It's really recognizable. But those electrons, or those hydrogens, go through kind of that funnel. And at the bottom of it, there's another, it's like a, he calls it a turbine. Yeah, it's like a turbine. And like through some sort of like voodoo innate magic, it just makes ATP. It like combines those hydrogens with ADP and spits out ATP. And that's really legit. And that's really cool. And that's why we keep living. So another picture, NADH coming into number 1. FADH goes to number 2. NA number 1, 3, and 4 help create the gradient. Number 2 does not. Number 4 is the one that makes water. And the FOF1, or the ATPase, is the one that makes ATP, right? It's in the name. One other thing about this that got overlooked, and when I took the test, bless you, I was like, what the heck is that? Number 4 has an iron copper cluster. Okay, it's like in the tiniest little freaking print.
Yeah.
It's got an iron-copper cluster, whereas the other three have an iron-sulfur cluster. So that's one of those, like, it's different. So if he asks you which one has copper, it's going to be complex 4. And he could ask you what's another name for complex 1 or 2, and that's going to be really easy because it's going to be NADH dehydrogenase or succinate dehydrogenase, which is just going to go to the fact that you already know it's NADH and FADH2. And that's pretty much it. And it's that simple. It's really not that bad.
Complex 4's enzyme is also known as succinate dehydrogenase for both of those. 2 and 4.
I would say 2 main, like I go by the picture, personally. So I would say, in my opinion, I would say that 2 more so than 4, just because it is directly dealing with that FADH2. But once again, I'll ask him where those discrepancies are. Exactly. Cool. All right. Once again, know the order, right? Know the order. It's in here in highlighted, bold, multiple different ways. So know this order, please. And there are blockers of this. Okay? We'll start here at this last one. So these, we have, was that cyanide and carbon monoxide, right? Carbon monoxide poisoning, like the silent killer, right? It's not good. There was actually a board's question of what has a higher affinity to hemoglobin, I think was the answer. That was a question. And I put carbon monoxide just because I'm pretty sure once that happens, like it's irreversible, right? That's not going to change. So that's why having CO leaks in our house, not good. You should probably get those checked about once a year. That's what Dr. Perryman said in our class, like get those things checked because you will be dead and you won't know it. So that uncouples going from cytochrome A and A3 into oxygen. All right, so that is our last block. So we will not be able to produce water here. So antimycin A, once again, I don't know why it's named this way, but it's between B and C1. So if you want to just think like A is between B and C, right? You get all the letters, you get your most bang for your buck. Antimycin A blocks it there, whereas retinone doesn't allow us to take that NADH and turn it, and it doesn't allow us to remove that hydrogen off of NADH and pump that hydrogen and give that electron to coenzyme Q. So it blocks that first step. So retinone, I like how I remember that one, is at the end of it, it's 1. So it blocks step 1, removal of that electron and hydrogen, and gives it to coenzyme Q. And then A, antimycin A, is between B and C1. And then carbon monoxide deals with the oxygen. Is there anything else? Here, real quick, 3 hydrogen ions coming down that FOF1 ATP synthase is required to make 1 ATP. It's endergonic. It's an endergonic reaction, creating that proton barrier, that proton gradient up here. That's endergonic, right? We have to put energy in. We're going against the gradient, so that requires energy. Whereas just those hydrogens going down is exergonic, because it's just going along that gradient super easy. And that,
Complex 5 is exergonic?
yes, should be. That is called the chemi-osmotic model because it deals with like a chemical gradient and the osmolarity, whatever. Chemi-osmotic, know that word. Describes coupling of electrochemical gradients to ATP synthesis. couple other uncouplers. We have 2,4 dinitrophenyl and carbonyl cyanide P, FCCP. You should see it on the test as FCCP. So those also uncouple between the electron transport chain and oxidative phosphorylation. And those stop ATP biosynthesis, but they don't interrupt the electron flow. So these uncouple the actual production of ATP, whereas the other ones were within that electron chain. This was on our test when we took it. Brown adipose tissue in newborns contain large number of mitochondria and also high cytochrome levels, but it oxidizes the fuels but does not synthesize ATP because it doesn't couple the electron flow with oxidative phosphorylation, and that's because of thermogenin. I think that was, oh, sorry, y'all can't see that. Thermogenin was on our test, and that's the reason that babies, their brown adipose tissue is different than our adipose tissues because that presence of thermogenin doesn't couple the oxidative phosphorylation together. And that's chapter 11. Not that bad. 25 minutes. Boom. Questions? Are there questions on that? Take 5 minutes, palpate, or leave, go to Dr. Denisa. Cool. All right, let's see if we can get out of here by 6:30. Yeah, I have faith in me too. All right, let's bring it back real quick. Bring it back one time. Two hop this time. Can only get to that song like 2 minutes before I want to like turn it off and change it. Can only do the same thing over and over and over and over again. All right, chapter 12, metabolism of other sugars. We have other sugars in our body? What? There's more than glucose? How freaking dare they, right? Speaking of sugars, national board question was, what is lactose comprised of? Galactose and glucose. Boom, go, next question, right? National board question, what type of bonds is amylose composed of? Alpha 1,4, yeah, you know. Yeah, you know, right? Alpha 1,4, amylose. Amylopectin is longer, so it's got alpha 1,4 and alpha 1,6, right?
I knew that.
Exactly. Not that bad. There were, we're going to start at the end of the chapter. I'm going to do something a little different. I'm going to experiment on you guys. We're going to start on page 153, and we're going to start off with the pentose phosphate pathway. 3 national board questions on just this one pathway. Can you believe that?
Wow.
Right? So we're going to start with this. It took me a while to understand this because I was like, where does this play any role into what's going on? We just went through glycolysis, right? So glucose is oxidized via glycolysis. What happens is there's this other pathway, the pentose phosphate pathway, that also metabolizes glucose. All right, so whenever you're thinking pentose phosphate pathway, first thing, we are metabolizing glucose. So it's either glycolysis to get energy, or we're going to go through this pathway. And the whole purpose of this pathway, there's like just huge buzzwords. It's going to be nucleic acid biosynthesis or reductive biosynthetic pathways. All right. So whenever you see the word biosynthesis of DNA, RNA, or any or those sugars for those, ding, 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 PPP, pentose phosphate pathway. It's also called the HMP shunt, which is on the next page, so you don't have to write that down. But biosynthesis of something, ding, 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 PPP. All right. So this, the other 2 big buzzwords are things that you should be on the lookout for pentose phosphate pathway is instead of using NADH, it uses NADPH. Okay, I would scoot it up, but it kind of stops me. So this uses NADPH, right? So PPP uses pH. And also, it produces ribose 5-phosphate. So what pathway? So the 2 things of like what it makes is NADPH and ribose 5-phosphate. And those go on to help with biosynthesis of other stuff. All right, that was pretty much 3 test questions on national boards, which is ridiculous, but that's what they want, apparently. All right. This was on Dr. Sarkar's test when I took it, and there are some people that got confused with it. So let's just walk you through this real quick. I have it written out on a different sheet of paper just so it's a little bit away from all the other big scary words. All right. We have ratios of NAD to NADH in our body, and we have ratios of NADP and NADPH in our body. Okay? And based on what our body's trying to do, those ratios are going to be a certain way at natural homeostasis. First off, let's start with NAD and NADH. We want this ratio to be high. What that means is that we're going to have way more NAD than we are going to have NADH. And that's because we're going to drive glycolysis to happen. All right, so when we eat food, we want to go through glycolysis to oxidize that glucose, right, and break it down, form that water, give off that CO2, right? So that high amount of NAD compared to NADH, I just put arbitrarily 100 to 1, whatever, that's going to drive glycolysis. It's going to drive that breakdown of glucose. Okay, so we want that high. And that was the test question. Like, do we want, he'll have like NAD, he'll have these ratios, and he'll say he wants this one high, this one low, this one's low, this one's also low. So like, you'll just have to figure out like which one is the right one. Now we have NADP, NADPH. So when we see NADPH, what are we thinking? PPP, also what are we thinking? Biosynthesis, right? Biosynthesis. Whenever you see a pH, you're biosynthesis. We're going to go make something, all right? We want this ratio low. So that means we have more NADPH than we do NADP. Okay? Why is that? That's because if we need to make something, we want to have that NADPH already there to give that hydrogen off and help make it already. All right? So if we're up a creek, we want to have that paddle. We want to have that NADPH as opposed to just being, you know, screwed whenever we're trying to make something. So understanding those ratios, like I said, that was a test question when we took it, but kind of a big deal. Does that make sense to y'all? Is anyone confused on that? Okay. Is everyone good on that? I want to hear yeses. If I don't, okay. Good. Good. So we're going to see a recurring theme here. Oxidation of glucose generates NADPH instead of NADH. It's also called the hexose monophosphate shunt, or HMP shunt. That's what they used on boards instead of just the pentose phosphate pathway, because they try to trick you. And generates ribose 5-phosphate for nucleic acid biosynthesis. Biosynthesis, boom, we already know. And that goes to make RNAs, DNAs. All right, I hate paragraph words like that, so we're going to have a picture. This is what's happening. This chapter is going to be a lot of just breaking down glucose or fructose or mannose or whatever, and it's not that bad. There's just like 4 things that I'm throwing at you at once, and there's just a lot of like fructose 1-phosphate or like fructose 6-phosphate or glucose 6-phosphate here and 6-phosphogluconate. So this one is more of, it's less of like a flow, as like glycolysis was just, all right, just like memorize the order. This one's like there's only 2 or 3 steps for each one, and it's going to be figuring out if it's a 1 or a 6 or if it's a fructose or whatever. All right, so when you're looking through this, just know that you're probably going to have to go back to this a couple times and just get those numbers and those words straight. But I'll try my best here. So we are turning glucose, and we're going to make it glucose 6-phosphate. And what we're going to do first is we're going to have, there's an enzyme which is glucose 6-phosphate dehydrogenase, right? But instead of making NADH, we're going to make NADPH because we're in the PPP shunt, okay? That's going to turn glucose 6-phosphate into 6-phosphogluconate. And then we're going to put that through 6-phosphogluconate dehydrogenase. And we're going to make another NADPH, right? Dehydrogenase, transfer of hydrogens. And that's going to be turned into ribulose 5-phosphate. Ribulose 5-phosphate, is it a ketone or an aldehyde? Ketone, right? Why? How can you just immediately tell? Ulose, right? Easy. So if we're turning ribulose 5-phosphate into ribose 5-phosphate, what type of enzyme reaction would that be? What kind of category would that be? An isomerase. Exactly, right? We're turning it from a ketone to an aldehyde. So you already know what this is going to be. It's going to be, it's going to have isomerase in it, and ribose is, how many carbons does ribose have? 5, right? So we're going to see something probably with pento or penta. and there's a phosphate on it, so it's probably going to be something with a phosphate in there as well. Oh look, pentose, isomerase. So if you don't even need to freaking know what the enzymes are, you already know it just by looking at the order of the stuff, right? Just looking at the words. So that enzyme converts ribulose 5-phosphate into ribose 5-phosphate. Whenever you see that, PPP, HMP shunt, nucleotides, biosynthesis. And that's it. And here's just another way of seeing it. It shows you the structures. All right, so glucose 6-phosphate to glucose 6-phosphate dehydrogenase. Right, we're going to make that NADPH. Boom. Then we're going to make NADPH again with another dehydrogenase enzyme, or lactinase, I guess, if he wants to get hard on that one. Whatever. I don't know what that actually. No, we're going to make here glucose 6-phosphate. Well, just use the first one that I said. 6-phosphogluconate dehydrogenase. Boom, it makes NADPH. Then it makes ribulose 5-phosphate. Then we have phosphopentose isomerase makes, that should be ribose 5-phosphate, not ribulose, as far as I'm aware. So check that. I changed it. But based on the fact that the other one makes ribulose, that one should be ribose. Cool. And really that's all there is of the important parts of the PPP shunt. There is a second part. I don't really remember there being much about this. There wasn't anything about the second part on boards, that's for sure. I don't remember his test having really anything big about this second part, so just read this on your own. All right, I'm going to just keep going through the material. Yeah, and there's pictures here. So significance, just to hammer it home, NADPH for biosynthesis of macromolecules, ribose 5-phosphate for nucleic acid biosynthesis. When is ribose 5-phosphate not needed? When PPP results to NADPH per glucose 6-phosphate. I got to read that one more time. When is ribose 5-phosphate not needed? PPP results to NADPH per glucose 6-phosphate. That makes no sense to me as I'm reading that right now. I'm sorry. I'm just like completely blanking on that. Okay, y'all can ask him that in class. Like, why is that important? I don't ask about that regulation. I don't think he asked that on our test though. Ribose 5 is needed when ribulose forms ribose. I don't think those are too big. And this is just talking about those ratios that we talked about earlier, where we want a low NADP to NADPH ratio because we want to have NADPH already made, right? So we can use it to build stuff. Boards, Wernicke-Korsakoff. Know this now. All right, this is in other classes as well. Wernicke-Korsakoff syndrome is caused during severe deficiency of vitamin thiamine. Thiamine is what B vitamin? B1, right? Great, good job, good job. If I had dum-dums, I'd give it to you. I owe you one. I owe you one. I have where are they? Tootsie Rolls in my backpack too. Would you rather have a Tootsie Roll? No? Okay. Bring that later. The active form of thiamine is thiamine pyrophosphate, TPP. What kind of reactions do we use vitamin B1 for? Where have we seen TPP before? Anybody?
PDC.
Yeah, so pyruvate dehydrogenase, right? That was one of our B vitamins used there, our coenzymes. But what type of dehydrogenation or what kind of type of reaction is TPP specifically used for? Decarboxylation, right? So our decarboxylation is going to be our B1. All right, so if we have Wernicke-Korsakoff syndrome, we don't have vitamin B1, so we're not going to be able to do pyruvate dehydrogenase complex, right? So that's not good. We're not going to have that enzyme to do any kind of decarboxylation reaction whatsoever. Not good. This is very bad. It's a genetic disorder that decreases the operation of this pathway as well. Okay? So you can't go through glycolysis, and you also can't go through this other way of breaking down glucose. Not good. Okay? You're going to have some supplementation for that. And that's pentose phosphate pathway. Not that bad. Glucose, biosynthesis, ribose 5-phosphate, NADPH. Whenever you see NADPH, biosynthesis, done. Wernicke-Korsakoff. All right. Next, let's do fructose. All right, we eat fructose too. What is glucose and fructose make? Sucrose, right? Sucrose. Test was 2 weeks ago. Last week. Was it last week? Test was last week? That was, yeah. So like they asked lactose on our boards. They could easily ask sucrose or maltose, right? You could easily ask any one of those. Long-term memory, guys. Metabolism of fructose. It happens in 2 different places. All right? It happens in our muscle, and it happens in the liver. I'm going to try something. I'm going to come over here and see what happens if I stand here. I've always wondered why professors do this. I can't see anything. All right, it's going to be great. All right. So we've got fructose. So let's start in the muscle, right? Let's start easy first. There's only like one step. In our muscle, we have a certain enzyme. And what enzyme is that? I'm pointing to it to give you a hint. Hexokinase, right? So remember when we learned at the beginning of glycolysis that hexokinase happens where? It's everywhere, right? But it's in the muscle too. And what was the enzyme that was in the liver? Glucokinase, right? Comparing and contrasting these right now, the first enzyme in the liver is going to be fructokinase, right? Because it's more specific. So we have glucokinase and we have fructokinase. Big deal. So he could ask, so when you're reading these test questions, make sure you know where you're at. If you're in the muscle, hexokinase, boom, done, right? Muscle needs energy, so it's going to just use that general enzyme to break down either glucose or fructose. Where it's in the liver, liver is more specific, right? It's got that glucokinase, it's got that fructokinase as well. All right, so in our muscle, it's going to turn fructose into fructose 6-phosphate, boom, glycolysis, done, right? Fructose 6-phosphate, so it doesn't go through, hexokinase, phosphohexosisomerase, and then, what is it? PFK1. So this just jumps right in. The next time is going to be PFK1. Add that second phosphate on. Boom, done, ready to go. Muscle, easy. Liver, a little bit more difficult. But end game to get it into glycolysis. Okay? End game is trying to get these things into glycolysis in as few steps as possible. So in the liver, it's more specific. Fructokinase. Okay? We're going to use that ATP there, making fructose 1-phosphate. All right? If it made fructose 6-phosphate, it'd be easy, right? It'd be just like in the muscle, but it's not. Okay? Fructose 1-phosphate. Fructose 1-phosphate is then gonna, whatever, it's not that big of a deal, but it's gonna go from this cyclic form into this open chain form, whatever. And then the next enzyme is going to be fructose 1-phosphate aldolase. All right. What did aldolase do the last time? It split them in half, right? It took what was it? Fructose 1,6-bisphosphate and made glyceraldehyde 3-phosphate and dihydroxyacetone phosphate. I always like to forget that one for whatever reason. All right. Well, it's going to make glyceraldehyde and dihydroxyacetone phosphate. So it's pretty much going to make the same things because it's made of the same stuff as glucose is. So that glyceraldehyde is going to get a phosphate put on it, right? So it can make glyceraldehyde 3-phosphate, boom, glycolysis. Done. Okay? And that's going to be glyceraldehyde kinase. Kinase, transfer of a phosphate group, right? Pretty simple. Man, I wish I knew this stuff as well as y'all going to know it for this test. That would be great when I took it. That'd be wonderful. All right, dihydroxyacetone phosphate. we can just put that through our regular glycolytic enzyme, right? Triose phosphate isomerase, and boom, it's already in glycolysis with that. All right, so really there's only two enzymes you need to know. We have the fructokinase, which turns it into fructose 1-phosphate, and then fructose 1-phosphate aldolase. All right? However, there's some other options over here. This glyceraldehyde can get turned into glycerol, which can then go to our lipid synthesis. Okay? So that enzyme is going to be pretty important with alcohol dehydrogenase. So alcohol dehydrogenase is going to take glyceraldehyde and turn it into glycerol. And say that we didn't, for whatever reason, we didn't want to convert that into lipids, we can take that glycerol and convert it into glycerol 3-phosphate, and then convert that glycerol 3-phosphate into dihydroxyacetone phosphate glycolysis. And those enzymes are glycerol kinase, glycerol phosphate dehydrogenase. Okay, so whenever we see glycerol, that means we're taking glycerol and turning it into something that can go into glycolysis, and the alcohol dehydrogenase is going to make glycerol. Like I said, this is just going to be kind of a bunch of different pathways that you're going to need to go over here in the next couple days just to refresh and kind of get your head around like what each of these are. The big ones that he likes to ask, he kind of likes to ask the first step in each of these. So he'll ask like, what's the first thing made, or what does fructokinase make? And you got to know that fructokinase is in the liver, so it's going to make fructose 1-phosphate. Or he'll ask you, what does hexokinase make? But you already know that, right? You already know that hexokinase makes, it puts it on the 6 carbon. Easy peasy. Okay. And I've gone over all this. Cool. Galactose. Galactose plus glucose equals what? Lactose, right? Galactose is a what epimer of glucose? 4. Mannose is 2. Also a board's question, right? So they can just pick whatever they want out of this freaking book. Dr. Sarkar's book is gold for boards, all right? It's gold. Also, you take Irene Gold board reviews. Irene Gold board reviews were not helpful really at all for, I can't say that. Well, for biochem, I thought it was like less helpful because they just like blow through it and they say, oh, like everyone sucks at biochem, so like whatever, like it'll be your best one because everyone else sucks at it, which is not helpful. But just watch my videos, watch the test reviews. That'll be like your easiest 2 hours. 2 hours at a time. It'll cover a third of the book. Galactose metabolism. Galactose, C4 epimer. The answer was on the board for y'all. You're welcome. Galactose is a milk sugar. It's metabolized in the liver, okay? And it requires 4 enzymes, 4 reactions to get into glycolysis. So like I said, the whole thing is to get galactose, turn it into glucose. And here's how we're going to do it. We're going to use galactokinase. That's a shocker. That we're going to do that, okay? So when we see galactokinase, we're going to make it galactose 1-phosphate. So we've already seen fructokinase makes it fructose 1-phosphate. Galactokinase makes it galactose 1-phosphate. Hexokinase was fructose 6-phosphate. Okay, can y'all see a theme there? All right, this one is a little weird because there's some like intermediates. So we've got galactose 1-phosphate now. We're going to turn galactose 1-phosphate into glucose 1-phosphate. And we're going to use this UDP glucose as a means to do that. It was kind of like how we used, what was it, in the previous chapter. It was kind of like how we used, we used something to, I can't like focus right now. Dihydroxyacetone. We use dihydroxyacetone phosphate to help convert NADH with the glycerol 3-phosphate. No, that's not right. Whatever. Forget that. Fast forward. Forget that. Think of UDP glucose kind of like as a coenzyme, all right? And this is just going to swap. They're just going to swap what they have. So we're going to go from galactose 1-phosphate to glucose 1-phosphate. So we're going to swap the galactose and the UDPs. Okay. This was on boards too. What is intermediate that helps convert galactose into glucose? And they wanted UDP glucose, all right? And Dr. Sarkar loves UDP glucose for that reason. Okay, that enzyme that converts galactose 1-phosphate into glucose 1-phosphate is galactose 1-phosphate uridyl transferase. Okay, uridyl U transferase. Okay, cool. And then we have over here, we have our UDP galactose 4 epimerase, which converts this UDP galactose back into UDP glucose so that we can keep that process going. Okay, UDP glucose, those enzymes, very, very, very important. So now we've got glucose 1-phosphate. We're so close. We're probably going to turn this into glucose 6-phosphate. That makes the most sense that it can just go into glycolysis right there. And that's exactly what happens when we're going to use the enzyme phosphoglucomutase to do that. Remember in glycolysis when we used, phosphoglycerate mutase to convert 3-phosphoglycerate into 2-phosphoglycerate? So that was a mutase, right? It was just changing where that phosphate was on that phosphoglycerate. It's the same principle. We're taking that phosphate from the first carbon to the 6th carbon.
Going back to that UDP glucose, what did you say was the importance of it?
It has glucose on it.
It has glucose on it.
Yeah, so this has, it's glucose, right?
Right.
So we've got glucose with this UDP on there. There's this uridine on there.
Okay.
So what we're going to do is this galactose has the phosphate on it. So we're going to put that phosphate on the glucose, and we're going to put the UDP on the galactose.
Okay.
So now we've got a glucose with a phosphate on it, and we've gotten rid of the galactose because galactose doesn't go into glycolysis, correct?
Right.
Cool. So that's what we did. I probably could have explained that a little bit better. Does that answer your question?
Yeah.
Good. And defect in any of these enzymes can cause galactosemia, so too much galactose in our blood, in our urine, not good, right? Not good. Any accumulation of excess in our blood, not good. If we ever see protein in the urine, not good. Protein should be filtered by the kidney, so we should be thinking kidney. If we ever see sugar in our blood, what are we thinking? Diabetes, right? We're seeing glucose? Yeah, so.
How do we know what, sugar in the blood or sugar in
Urine, I'm sorry, it should be urine. Should be urine. Yeah, you should have sugar in your blood. That'd be good. That'd be very good. Very not bad. But that's, you'll get to that in try 5. All right, Mannose, and that's it, and we'll get you the heck out of here. Last one, Mannose. Mannose is a C2 epimer of glucose. All right, C2 epimer. I forget which one it is. It was either Mannose, they asked Mannose or galactose on boards. And that's where it is. The hydrogen's on the wrong side for Mannose, right? It's over here. What an idiot. It's on the wrong side. Oh my gosh. This one's only got 2 steps. All right, we've got hexokinase. All right, hexokinase. If we see hexokinase, what carbon do we think that phosphate's going on? 6. Boom. Mannose 6-phosphate. Easy. Then all we have to do is turn that into something that can go into glycolysis, and there we use phosphomannose isomerase, making fructose 6-phosphate. So instead of phosphohexose isomerase, it uses phosphomannose isomerase. That was like the worst one. So difficult. And that's it. That's the chapter, y'all. Any questions? No? Is there something y'all want me to go over one more time real quick? No? Yeah?
Can you just speed through the pentose phosphate pathway one more time?
For sure. Pentose phosphate pathway. What words are we just going to key on? Biosynthesis. Exactly. What else? NADPH. Anything with a P in it. All right. And what else? Which one? Ribose 5-phosphate. Ribose 5-phosphate. Okay. Do we want a low or high NADP to NADPH ratio? Low, right? We want to have a lot of that NADPH ready to go, right? Yes. Because we want to make stuff, and it's my money, and I need it now, all right? All right, so we're going to start off with glucose 6-phosphate. So we've just put a phosphate. We probably use hexokinase first to make that happen. Just kind of a little deductive thinking there. Chiropractic is an inductive or deductive science. Did y'all learn that in deductive science, right? We're just starting with what we know to be true. Innate intelligence controls the body and everything that it does, and we go from there, right? Okay. Glucose 6-phosphate. Let's make some NADPH right away, all right? There's really the two big steps. And so we're going to go through glucose 6-phosphate dehydrogenase. Dehydrogenase, we're in the PPP pathway. It's going to make NADPH, right? And that's going to make 6-phosphogluconate. And then we're going to go through 6-phosphogluconate dehydrogenase. We're in the PPP pathway, HMP shunt, NADPH. Okay, and that's going to make ribulose 5-phosphate. Ribulose is a how many carbon sugar? 5. Ribulose is the aldehyde or ketone? Ketone, right? Because it's a ulose, and we need to turn it into just ribose 5-phosphate. So we're going to use an isomerase enzyme to do that, to turn that ketone into the aldehyde. So it's going to be phosphopentose isomerase. You can get all that just from the pathway itself. Okay? And that's really the big part of everything. And that's going to go make your nucleotides, your coenzymes, your DNA, your RNA. It's going to biosynthesize. Is a biosynthesis going to be catabolism or anabolism? Anabolism, right? We're going to add stuff together to make something. Cool. And then, like I said, the second part doesn't really stand out to me. Just read it on your own. Honestly, don't know that little part like the best. So just be me reading off the page, which I don't think you want me doing. You can read it off the page yourself. Cool. Go home.